Today I'm going to do some cooling system maintenance on my Volkswagen Golf. I'm going to talk about the 8 different cooling system components, how it functions, and also show you how to replace the hoses, the thermostat, and flush the system and replace the antifreeze coolant. The purpose of the cooling system is to warm the engine up to a temperature that makes combustion and operation most efficient, and then it maintains that temperature no matter what the outside air temperature is or how much load is actually on the engine. When you start the engine and the metal parts in the engine are still cold, not at the optimum temperature, the air-fuel vapor that comes in to the engine tends to condense inside the cold metal parts inside the engine, and what happens is that you get inefficient combustion, you get deposits, carbon deposits on the inside of the engine, you get this quenching where the quench area of the combustion chamber will cause the vapor to condense, and then you get liquid fuel droplets in the engine, and that won't burn. So on the exhaust stroke, that fuel gets ejected into the tailpipe, out the exhaust port. So that is just unspent fuel, and that will increase your emissions, and it will increase your fuel consumption. So you want that engine to be warmed up as fast as possible. So when the engine is warmed up and operating efficiently, when the fuel combusts, it releases energy in the form of heat. Now, air fuel that enters the engine is typically like 14.7 pounds of air for every pound of fuel. So there's a lot of air that enters with that fuel that gets heated up and expands, and that produces pressure and produces makes the engine do work. But there's a lot of heat. Only 30% of the energy in the fuel goes towards this mechanical motion of the engine. Another 30% of that energy gets converted to heat and is lost out the exhaust pipe or the exhaust port, and another 30% of that energy in the heat it gets delivered into the cooling system, and the cooling system has to cool the engine down, and then another 10% or so of the energy is lost for friction and stuff like that. So considering this 30-30-30-10 split, when you need more energy because you want more power to go up a hill, you got to put the pedal to the metal, you burn more fuel, so you get an increase in energy going towards propelling the engine, but you also get more energy going out the exhaust pipe, you get more energy going into the cooling system. So all of the extra energy that the engine needs to dump to get rid of to keep the temperature regulated, the cooling system has to regulate that. The components of the cooling system are the water pump, the thermostat, the hoses, the radiator fan, the heater core inside the dash that gives you cabin heat, the coolant reservoir, which sometimes is an expansion tank, other times it's just a reservoir, and the pressure cap, and the coolant itself. An engine is actually hollow. It's surrounded by a jacket of water. There are a lot of passages throughout the engine called water jackets. But this water around the engine, as the water pump turns, it always moves that water through the engine and keeping the temperature consistent throughout the engine, even though most of the heat is up in the head where the combustion occurs. So the engine is always maintained at a constant temperature, like say 190 degrees Fahrenheit. And when the thermostat feels the water getting hotter than that, it will open up and divert some flow of water into the actual radiator, and then air passing over the radiator will remove some of the heat and cool down that water, and then that water is circled into the engine, and that's what regulates the temperature of the engine. This is a water pump for this car. The V-belt pulley goes on here, and as the engine spins, it spins this impeller around, and this impeller, there's a housing that goes on right here, and water is drawn into the housing then and ejected, and that's what creates flow and pressure. The pump also has a bearing and a seal and a drain. So as you can see, there's a lot of pink goo on this particular pump. What happens is, as they age, several things can go wrong. One is that the seal will start to leak, and then coolant will start to flow out the drain and will start to make a lot of crusty antifreeze all over the pump. Another thing can happen is the bearing can actually go after a while. This particular pump has an okay bearing. If you were to listen to it spin, it's pretty good. But now, This is another pump. The same thing again. This pump has a bad bearing. Listen to this. When the water pump bearing goes, the thing sounds like a skateboard, a rough, rumbling noise. You can't miss it. And you want to obviously replace the pump once the bearing starts to rumble. Another thing that could cause a pump to fail is erosion due to cavitation. What cavitation is you can think of it like the propeller on an outboard motor on a boat. As that propeller spins in the water, it's like a screw going through water. Now, that screw, if it slices through the water nice and clean, everything is great. But if something were to happen and that screw, that propeller were to spin faster than the water would permit, what would happen is bubbles would start to form. It's almost like a wood screw that's turned into wood, but it starts to strip through the wood. Well, the propeller starts to strip through the water. And what happens in that particular case is there's not enough water is probably being drawn into the pump, and the pump itself is trying to suck, and the suction side of the pump is creating a very low pressure and trying to draw water in. And when that stripping of the water happens, bubbles are formed. And those tiny, tiny bubbles are created due to the low pressure. And when those bubbles burst, when they contact the metal, what happens is the bursting bubbles create a little shock wave that could be like 60,000 psi of pressure. And that shock wave then tends to eat away the metal. So you can see this on boat propellers or lots of objects like pumps. And this cavitation, because aluminum is a soft metal, tends to erode away the aluminum in the pump. And then that aluminum bits and particles can end up being lodged in the radiator or different parts of the system, and then you have to replace the pump. So it's a good idea to make sure that the radiator is flowing very well and the pump can draw water very easily from around the engine or the radiator in the system, and that everything is functioning properly and well. The next part is the thermostat. It looks like this. Inside there's a wax pellet, and what happens is this wax pellet is on the side of the engine that senses the water temperature inside that jacket in the body of the engine. And as the water circulates through the engine, this wax bulb inside, this tends to sense the temperature. And this is a valve. When it gets hot, the valve will tend to open up, and then the flow of water can then go through the thermostat and enter the radiator. Now, if this guy were to break, say it got stuck open, what would happen is when you start the engine cold, the water would start going through the thermostat immediately and entering the radiator, and it would take a very long time for the engine to warm up. In the winter time, if it's very cold, the engine may not warm up at all, and therefore you're going to have all the problems that we already talked about. But if the thermostat were to break and say get seized up and not open up when it's sensed hot, what would happen is no water would flow into the radiator and the engine would overheat. Some people, what they do is they probably have an overheating problem, and what they do is they say, well, we're going to take the thermostat out and run the engine with no thermostat, therefore we get more cooling. Well, it doesn't work like that, and it's not going to work. That idea is the same thing as saying you come home and your house is dead cold and you're freezing, so you want 72 degrees room temperature, so you turn the thermostat up to 100 because you think that up to 100 is going to make the room warm up faster or something, when actually the room will just warm up as fast as it can anyways, and instead of turning off the heat at 72, it just keeps on raising past 72. So this thing works the same way. There's a number written on the thermostat, 87 Celsius. So that's 190 Fahrenheit. So this is a 190 degree Fahrenheit thermostat. That's when the thermostat starts to open. And by the time the temperature reaches 20 degrees Fahrenheit higher, 210 Fahrenheit, this thermostat will be fully open. The hoses are made of rubber and they are impregnated with some type of fabric. As hoses get old, they tend to deteriorate and crack up, and around the openings they will start to swell out, and that's where you start to get coolant start to crust and leak. Also, if they get really old, parts of the rubber can actually flake off, and when it does, it can be circulated around the cooling system and get lodged in the radiator and help plug the radiator. The radiator is a heat exchanger. So the hot water flows into the radiator, and then all these fins on the radiator tubing acts like a heat sink. So any surrounding air gets heated up by the heat inside the radiator, and then that removes the energy from the heat in the radiator and cools down the water. You always need fresh, cool air flowing over the radiator. When you're traveling at highway speeds, like above 60 miles an hour, the ram air that comes into the front grille of the car, that's sufficient to remove the heat from the radiator. But when you're in stop-and-go traffic, you don't have enough air flowing over the radiator. This fan will turn on and blow air over the radiator to let that air then pick up the heat. The fans are controlled by a thermostatic switch. So like right here, there's a switch, and that just measures the temperature of the water in the radiator. As that water gets hot, the switch will close. You can actually unplug the switch here and put a paper clip or something here to bypass it to test to see if the fans are working. But when the water gets hot enough, that switch will trigger the fans to turn on. So if you ever had a problem where your fans weren't turning on and the engine was getting hot, it could be a bad thermostatic switch. It would just be a matter of draining the coolant, remove the switch, and screw in a new one. Another thing to remember is that the radiator is actually a big filter. The incoming air from the front of the car, it acts as those fins act like a great filter to squash and pick up any bugs or mud. So you always, when you're washing your car, you always want to make sure that you're washing all that stuff off the outside of the radiator. On the inside, any debris you have in the system, like for example, if you're using antifreeze that has silicate in it, and it's old and it's starting to precipitate out and create like silt, goo, it can deposit in the radiator, as well as any other debris like aluminum or rubber. All that can get trapped in the radiator and create a blockage. The coolant ball is just a reservoir. As the engine gets hot, the coolant tends to expand, so it needs to flow somewhere, the extra volume, so it tends to fill up the ball a little more. When you shut the engine off, the engine cools down, the water tends to contract a little, so it will draw water out of the ball again and into the engine. This is a closed system, and it has a cap. So this pressure cap then has a valve, and this will regulate the pressure to be a maximum of something like 15 psi. If the pressure goes above that, rather than have hoses burst, this pressure cap will then just eject any coolant onto the ground. But the pressure cap on other cars, on the radiator, you've got this cap, and under the cap you've got a hose, and then that hose runs into an expansion tank. And how that system works is you don't have a closed system like this, but rather the radiator is filled with antifreeze. And if the system gets above 15 psi, the spring-loaded cap will let the pressure blow off any extra antifreeze coolant into that overflow tank. And then that will always keep the system at 15 psi. Now, when you shut the system down and the system cools and the antifreeze contracts, there's a vacuum valve on the bottom of that pressure cap. And what happens is the cap, the system, as it contracts and sucks, it will suck antifreeze back out of that expansion tank in through the cap and into the system again. So the question then is, why 15 psi? Why any pressure at all? Well, if the system operates under pressure like 15 psi, that can help avoid and prevent the cavitation problem with the water pump. But another thing that happens is you want to run the engine at around 190 degrees Fahrenheit. So that means the water that flows out of the top of the engine and going into the radiator, that water is probably in around 200 degrees Fahrenheit, maybe higher. Now water is going to boil at 212 degrees Fahrenheit. If the water boils, you know the bubbles that form in the water, that's going to displace a lot of water. So that's going to drive water out of the system, and that's going to make the water in the system have less capacity to cool the system down. So what's going to happen is that the engine will tend to boil over if the water starts to boil. Now, even though water boils at 212 degrees Fahrenheit at sea level, if you pressurize water, it will boil at a higher temperature. This is why your grandmother's pressure cooker tends to cook food really fast, because in a pressure cooker you let the pressure rise really high, maybe 20 psi or something. And what happens is the water will then boil at not 212 Fahrenheit, but maybe 250 or 60 Fahrenheit. The hotter water will cook the food faster. For every 1 psi that you raise the pressure on water, you raise the boiling point of the water 3 degrees Fahrenheit. So rather than boiling the water at 212 degrees Fahrenheit in the engine, if it's at 15 psi, the water is going to boil at like 250 degrees Fahrenheit. So that gives the water in the engine extra margin to be able to pick up extra heat and never have to worry about boiling. It makes working on a system like this risky because if the engine is hot, you remove the cap, atmospheric pressure enters the container. Now all that hot water is going to immediately start to boil. It will boil out, it'll get on your skin, it's going to be 250 Fahrenheit, and it's going to give you a really nasty burn. This is why you never remove the pressure cap on the coolant system when the engine's hot. The last thing then is antifreeze. Not only does antifreeze prevent the water in the engine from freezing in winter, but it also raises the boiling temperature. On the back you'll see if you mix the stuff, so this is the raw antifreeze, not 50-50 stuff, so you have to put water with this. I'm going to use distilled water that I purchased at the grocery store. But if you mix this stuff with 50-50 and if the pressure cap is at 15 psi, well then you can get this stuff won't freeze until minus 35 Fahrenheit, and it won't boil at 15 psi, it won't boil until 264 degrees Fahrenheit. Now, if you try to mix this stuff richer, what will happen is it can freeze at minus 83 Fahrenheit and will boil at 277 Fahrenheit. But the thing is, when mixing this more than 50-50, so if you put more antifreeze in the system than water, the water is the actual part of the system that does the cooling. The antifreeze doesn't. So richer antifreeze mixture will actually give you less ability to cool down the engine. Now this antifreeze is Volkswagen, they call it G12 pink stuff, but it's based on organic acid technology. But all you got to know is that this stuff here doesn't have any silicate in it, doesn't have any phosphate in it. So it's a special type of antifreeze used by Volkswagen. The Volkswagen parts department wasn't open today, so I'm going to just flush the system out today completely and replace it with Prestone, which is also organic acid-based antifreeze that does not contain any phosphate or silicate. So what's wrong then with phosphate or silicate? The antifreeze does a couple of other things, provides protection against rusting, but also in this engine you've got a cylinder head that's made of aluminum, and you've got a block that's made of cast iron. So you've got two different types of metals surrounded by a jacket of water. Now if that water were to conduct electricity, what you've just created is a battery. The aluminum is the more corrosive metal in the mixture, and what would happen is the aluminum would dissolve and deposit on other parts of the system. So you need to protect the aluminum. One great way to protect aluminum is using silicate. The silicate paints over the aluminum and protects it from corrosion. Additives in the antifreeze also serve to balance the pH or the acidity alkalinity of the actual liquid, so the water won't conduct any electricity. But one of the problems with silicate, it has a shelf life. Typically after 3 or 4 years it will precipitate out and form a solid, and then that can obviously deposit in your radiator and create a blockage. Even like antifreeze that's on the shelf, if it's more than 3 or 4 years old, it's already probably starting to break down. So some people stay away from silicate and they use phosphate. Phosphate works great at preventing that water pump cavitation thing. But one of the things that Europeans don't like about phosphate, in Europe they have really hard water or something, and the calcium and the magnesium that's in hard water will tend to react with phosphate and will scale up the inside of the radiator. And therefore, I guess really hard water, they don't want to use phosphate in their antifreeze. They don't recommend phosphate antifreeze for another reason. When that silicate starts to break down, if there's phosphate in the antifreeze, you get hot surface corrosion. And what that is you get hot spots that may form around the exhaust valves. If the silicate is not around there protecting that aluminum, what can happen is that you can get the creation of aluminum phosphate eat away the aluminum in your head. You can get the cheaper antifreeze that has silicate in it and dipotassium phosphate and ethylene glycol and diethylene glycol, all that stuff. So this one here only has ethylene glycol, diethylene glycol, sodium 2-ethylhexoanate, and sodium neocyanate, whatever. But this is organic acid type stuff. Just, it's very similar to the antifreeze that's in the car now. But we're going to flush everything out before we put this stuff in. Get the carp in the air on jack stands, and then remove this splash guard. I'm going to take the alternator off, the serpentine belt, compressor for the air conditioning. So we just bring this guy out like this, and that relieves the tension on the belt. That can come off. Just remove this nut. Oh, there's a little nut down there. It's got 12 volts on it, so you want to wrap this in some kind of plastic bag. Preferably you'd undo the battery cable, the negative on the battery, but I don't want to have to reset the clock and all that shit, so I'm just going to wrap this up in a plastic bag like this. There's a bolt here and a bolt down there. This may help. That's your alternator. Now there's a bolt on the AC compressor right there, and there's one down below it. Now we've got to remove those so that guy can come off. Get your little magnet. Pick the nuts out. Alright. This thing should come off now. Okay. So that is off. Now what we've got here is, this is the water pump housing. This is that water pump. We don't want to take this off, but you can see down here, this little 90-degree elbow, this is the thermostat housing. So the thermostat lives in there. So we got to get this bracket off down here so we can actually unbolt this housing and remove it and get access to the thermostat. Okay, I hooked a bungee cord onto the pulley of the power steering pump. I'm just going to take it and, I don't know, tie it maybe, put it there. So when I take the bracket of it, that won't fall. So what we got then is this elbow. This is the thermostat housing. 1, 2 bolts. Take those 2 bolts out, and all that. Then the thermostat will come out of there, and lots of coolant will come in on the floor. To get the coolant out, what we're going to do is we're going to actually just undo this hose, which is the lowest hose in the system. That will drain out most of the antifreeze out of the radiator. But taking the thermostat out will drain the antifreeze out of the engine. Now we're going to undo that clip on that lower hose. Oh, one last thing what you want to do is go inside the engine compartment on the temperature cluster, turn the temperature control knob all the way to hot. You also want to, good idea to wear gloves doing this, because this stuff is not good on your skin. There we go. Let's put that hose back on now. Now we're going to undo that thermostat. Now it's just a matter of pulling down the thermostat housing. Now we pull the thermostat out, and then she's going to gush. So the next thing is to undo these clips and start removing these hoses, like the one up here. You take this guy off, take all these hoses off, just undo them and put the new ones on. So once you have all the hoses off, then you can go around and use some Scotch-Brite pad, which is just green abrasive pad like that, and go around, use some spray 9 or some kind of engine cleaner and clean up all of your steel or metal fittings. Next is the bottom radiator hose. So this is the bottom radiator fitting, and this is the thermostat housing that goes into the bottom of the water pump. The thermostat has an O-ring around it. It belongs on the thermostat housing, just like that. And then the thermostat goes like this. So what we're going to do here is take the thermostat off. We're going to take this and we're going to put it on like that, and then we're going to put this up. So now I'm putting back on the thermostat housing from the bottom side. Then we're just going to use the ratchet. I'm going to tighten this bolt here. Now I did not put the thermostat inside this because what we're going to do is we're going to fill the car up with water, plain old tap water, and we're going to run that a bit through the engine, and then we're going to drain that, and that'll be flushed. Then we're going to put the new antifreeze in. The next hose will be this one, this part where my finger is in here. That goes on right here. Okay. All hoses are put back now. The thermostat is not put in. What we're going to do is flush the system. So now we fill this up with water. Squeeze this hose. You should take more water. Now we want to spin the water pump to circulate the water. I'm going to use the chuck on the drill to pull the V-belt tight and spin it. This makes the water flow, of course. So now I'm going to pull that bottom hose off again and remove the thermostat housing and drain all this water out of the car. So what we're going to do is we're going to take the thermostat, the wax pellet side, and that's going to go in towards the hot water in the engine. Now, in the groove around the perimeter of the thermostat, we're going to put the O-ring. And then once the O-ring goes in, then we put the housing up. So that looks like that now. Now we just reconnect that bottom hose and put the clamp back on, and then the system is closed up. I'm putting back this bracket now. But in here we've got these bolts that come up through, and we got to put these nuts on. Now the challenge is, how are you going to get that nut on there? Here's a trick for you. Take a deep socket like this, take your telescopic magnet, put the magnet through like that, put it on the nut, draw the nut back. Now you can hold the nut in place while you feed it in, and then you turn it by hand. Okay, the power steering pump is now back mounted on. I just put back the AC compressor. That's just one bolt here and one bolt below. That's what puts this guy on. Now we reinstall the alternator. Battery cable goes on here. The tension relief strap goes on here. And the two bolts go in through here. That's it. Next we put the serpentine belt back on. Now it's time to put the V-belt back on. Put it around the pulleys. You can use a 22mm wrench to walk this guy up so it's loose as possible. Take the pulley, put it like that. Okay, how much to deflect? If the span between the two widest pulleys is between 7 and 11 inches, then it should deflect 1/4 of an inch. If it's like 12 to 16 inches span, then it's a 1/2 inch deflection. So we're going to go with these two guys here. I want to see this deflect like no more than 1/4 inch in the middle. If you get your belt too tight, you could ruin your water pump bearing. So you don't want to have the belt too tight. Tighten the lockdown bolt then. Splash guard can go back. Now comes time to fill up the antifreeze. So we have to mix this stuff 50-50 with water. So what I use here is distilled water from the grocery store. And I got a container here. I just fill it up to some level. There. Put it in the jug. And I do the same with the water. Now that can go in the car. Put some cardboard under the car or paper or something so you can easily pull it out and look for any leaks that may be leaking on it on the floor rather than having to crawl up and under the car. You want to keep doing this until the coolant ball doesn't go down anymore. Then we want to squeeze this hose. Another thing you want to do is have the car on the ground, because you got to keep in mind the point in the system that is the highest where the hose is, that's where air bubbles will be. So you always want to make sure that the coolant reservoir is the highest point in the system. If the level in the coolant ball doesn't want to go down, even though you've only added a few quarts, what you've got to do is you've got to squeeze the hoses. And you've got to squeeze these guys over and over and over until that level goes down. It will go down. It's going to take a lot of squeezing. As long as you keep squeezing the hoses, the water will keep going down. Well, that's how you do that. Keep the heat on max, drive around, put some load on the engine, get the engine hot, make sure the temperature gauge always stays in the middle and never higher. Stop the car every now and then, see if that coolant ball is getting low. Keep adding antifreeze or coolant to that ball, as long as of course the pressure is not getting too high in the system. Feel the bottom radiator hose to make sure it's getting hot. If you've got the top rad hose feeling hot and the bottom rad hose is starting to feel hot, you know that the thermostat is open and you're getting good flow. And make sure you're getting heat in the cabin, because then you know you're getting good flow in there also. All we needed was the 1 gallon of antifreeze and 1 gallon of distilled water, and that did the job. Thanks for watching.